Hello students, welcome to Physics Wallah, Gate Wallah. How are you? So I hope your preparation is going absolutely fine. And I'm Shivam Dikshit. I did my masters from NIT Calicut in thermal science. After that, I got chance to work with Indian Oil Corporation Limited (R&D) as automotive research officer. And very warm welcome in this series of basic thermodynamics, right? And we already covered few of the topics, right? So if you have not attended those lectures, like initial lectures of basic thermodynamics, then I would like to suggest here that please go and watch those lectures. It will definitely help you to understand the topic, right? And in previous lectures we already discussed what is the thermodynamics, what is the use of thermodynamics, what is the importance of thermodynamics, right? How thermodynamics is based on the laws, correct? And what we exactly do in the thermodynamics, right? What are the ways to learn the subject, like what are the like microscopic viewpoint, macroscopic viewpoint, what is the criteria to apply macroscopic viewpoint, that is concept of continuum. What is thermodynamic system? Thermodynamic system, quantity of matter or region in space, surrounding, boundary, type of boundary, right? Type of system, like open system, closed system. What is the criteria? How to identify it? Then after that we discuss the thermodynamic properties, which are the characteristics to define the system. And very important point we discussed, that is a properties are the exact differentials. That also we discussed. After that we discuss what is a thermodynamic state. Even we have a little bit idea about the thermodynamic process, right? So we are extending our discussion on the thermodynamic processes. Then we'll go for thermodynamic cycle, then thermodynamic equilibrium. So all those things we are going to finish in today's lecture. And whatever basic concept theory part is there, well, or we can say whatever basic requirements or basic definition part is there, that is going to over by today itself. Then in next lecture onwards we'll start our discussion on ideal fluid properties, ideal gas properties, and its mixture properties. Okay, so I hope you already watched the previous lectures of the same series, thermodynamics, right? So already I think 5 lectures already happened, right? This is a 6th lecture on the basic concepts, correct? So in previous 5 lectures, whatever we discuss, if you go through it, definitely it will actually help you to understand the subject. See, sometimes students are feeling that these basic concepts, these basic definition parts are not asked in the gate exam, right? Generally it is not asked in a gate, and why to study it, right? Directly we can jump to the first law of thermodynamics and work interaction, entropy, exergy and all. But my dear student friends, in thermodynamics the major problem is that if you read any concept, if you learn any concept, if you study any concept, then you can easily understand those concepts. You will feel that you actually understand, right? But when it comes to the solving the numerical problem, then you are not able to solve. Why exactly it is happening? Why exactly it is happening? Very simple logic is there. The simple logic is, you people are actually neglecting these basic concepts. If your basic foundation, basic definition, what is thermodynamic equilibrium, what is thermodynamic process, what do you mean by reversible, what is irreversible, right? If these things are not clear to you, believe me, it will be very difficult for you to understand the problem itself. Solution is a different thing, right? But even you will not be able to understand what exactly problem is defining, what exactly they want to ask. Clear? So that's why it's very important. And one another fact I can say, that you are not only going to give the gate only, right? Maybe you are preparing for gate, but after gate you may give a bark exam or ISRO exam, right? ISRO separate exam is there, even HPCL I think also taking separate exam, ESC exam is there, even a state government exam like assistant engineer exam, junior engineer exam. So you may give multiple exams, right? So in other than GATE, whatever exams are there, in that theoretical questions were also asked. So in that theoretical question, to answer the theoretical question, these concepts will help you a lot. Clear? So my suggestion is, my personal suggestion is, don't neglect this part, right? Don't neglect this part. It is equally important. Equally important, I would say. Okay, sometimes it's feel like it's a boring. Why unnecessary to study it, right? So but you have to, if you really wants to command in this particular subject, then you have to study this one. And my suggestion is, when you are studying this, either if you are studying this subject first time, then prepare the full notes. If you are studying a second or third time, in that you can at least prepare the short notes. Okay, now whatever important points we are discussing, at least you have to study, you have to write those points in your notes. Clear hai? Okay. Let's continue our discussion on the thermodynamic processes. So I already told you, thermodynamic process means a change of state. State is nothing but a condition of a system, and condition is identified by the properties. So at a particular state, all the properties of the system have a fixed and definite value. Fixed and definite value, right? Now if this state is going to be changed from state 1 to state 2, when this state is going to be changed from one position to another position, one point to another point, one state to another state, then this is basically called as what? Process. This is basically called as what? Process, right? So let's say if we represent any state in any property diagram, then coordinates are always property. For example, PV. We already know that in property diagram, the coordinates are always properties, whether it's a PV diagram, TS diagram, HS diagram, TV diagram, PS diagram, whatever diagram it may be, the coordinates are always property. You have never seen such a diagram like T heat diagram. No. P and work diagram. No, there is nothing like that. Even in some books, they are they actually did this, right? They actually did this to make you understand a particular concept, but in analysis point of view, those diagrams are not used. Only we are using the property diagram where the coordinates are always properties. In this case, if properties, like if any particular state we want to represent, so in a state, properties are going to be fixed on definite value. So I can say, suppose this is an initial point, so this is the initial property, I would say P1, and this is a initial volume V1. Now something is happening to the system, maybe some heat transfer, maybe some work transfer, or anything. Something is happening, and because of that, the, let's say, pressure is pressure is decreased and volume is increased. Now it is become V2 and it is become P2. Now this change of state from state 1 to 2, this change of state is basically called as what? Process. This change of state is called as what? Process, right? Now when system is moving from state 1 to state 2, then in between there may be possibility that multiple equilibrium states are there, right? So if we defined each and every state which are coming in the, like between the 1 and 2, and this series of equilibrium states through which a system passes during the process is called as what? Path of a process. That is called as a path of a process. Clear hai? Right. Okay. Now in thermodynamics, the process can be classified as a reversible process and irreversible process. What do you mean by reversible process? Reversible process means a process in which, right, in which the each and every equilibrium state is defined. In even better way, I can say that a process, if it is reversed, then the initial condition of system as well as surrounding can be restored. Initial state of system as well as surrounding can be restored. That is basically what? Reversible process. I hope you may have little bit idea about it, right? But one thing I can say you, that actually in practice, reversible process cannot be achieved. Why? Because if reversible process achieve, then the very fundamental law that time is always a unidirectional. Even nowadays some theories are there in internet, you will find that they are saying that time is a multi-directional. There is parallel universe theory, and in different universe, this is one universe, even other than this another universe is there. So in another universe another time pattern is there, something blah blah blah. But those are only theory, there is nothing proof in that, right? So, and those are not universally accepted also. The universally accepted one is that time is a unidirectional, means time is only moving in one direction, forward direction. It cannot go to the backward direction. What do you mean by that, right, sir? If you ask me, sir, what do you mean by that? Very simple logic I am telling you. See, you can go to the past only if reversible process is possible, and reversible process is actually not possible. It is only a theoretical thing. If you really want to go into the past, then reversible process is the only way. For example, let me make you understand clear that for example at 8 o'clock, right, 8 a.m. someone is died, some person, you know, this person, this is a some person is basically died, right, at 8 a.m. Now it is become 8:30. Now it's become 8:30 a.m. Okay. Now please listen here carefully. So this person is died at 8 a.m. Now at 8:30, when you get to know that this person is died, then you thought actually this person knows one region, right? One place where lot of gold is there. For example, just for example, this is the person. Now this person know actually a place, right? Actually a place where lot of gold is there. But before saying this, the place name to anyone, he died. Now no one knows where is the gold, right? No one knows where is the gold because he is died. Now it's become 8:30. Now you actually want, if suppose all the processes whatever happening that is reversible, if whatever process is happening, right, that is a reversible, then what you can do, that you can reverse the process, and system and surrounding both can restore its previous state. Now system and surrounding, here see definition what I wrote. Right here I clearly mentioned that system and surrounding may be restored to their initial state. Both, both system as well as surrounding. Now system plus surrounding is universe. Basically a process is said to be reversible process if if it reverse, then the previous condition of universe can be restored. Now what you are going to do, whatever process is happening, right, that process we are going to reverse. All the processes we are reversing, and if all the processes are reversible, then complete universe will be reversed. Right, now we can restore the condition at 7:30 a.m. for example. Now at 7:30 you will find that this person is actually alive. Now you can ask him, where is the gold? You are getting my point. But this is not feasible. This is basically not possible because reversible process itself is not possible. Just an hypothesis. So you may understand, you can understand this point, that a process is said to be a reversible process if it restored, then the previous condition of system as well as surrounding can be restored. Correct now? Or we can say complete universe is reaching to their previous condition. Okay, so that is basically what reversible process. Now the question is coming, when it is possible, how it is possible, right? Actually it is not possible, but theoretically what are the conditions to achieve it? Theoretically what are the conditions to achieve it? So basically two conditions are there to achieve reversible process. Two major conditions I would say. The very first condition is that if you reverse the process, then it must follow the same path. Because if it will not follow the same path, different path will be there, then definitely it will affect your system will change, because if intermediate points will be different, then something may happen to the system as well as surrounding. So the first very important condition is that if it is reverse, then follow the same path as that of forward path. That is the first condition. And obviously another one is without affecting the system as well as surrounding. Let me give you an example of one block. So let's say we have one block here, right? We have one block here. This is a block, right? This is one block, and it is at one particular condition. Let's say initial condition, that is 1. Now we are applying force here. And we reach to the 1 to 2, this condition. We reach from 1 to 2. This is the final condition. We started from 1, we reach to the 2, right? We started from 1, we reach to the 2. Correct. Now when we start from 1, we reach to the 2, right? So now some process is happening, obviously, right? And this system is going to follow some path. Let's say it is following this particular path, right? This particular path. Now please listen here carefully. This process is said to be a reversible process. If it reverse, then whatever happened during 1 to 2, every single phenomena should be reversed with the same magnitude. Every single phenomena is reversed with the same magnitude. For example, see here, you just tell me what is happening during 1 to 2. During 1 to 2, what we are exactly doing? We are applying force and block is moving, means work is done. Action of force on a moving body is work. No, we already discussed in previous classes. So when we are applying force here, then what is happening? This block is basically moving. So actually we are doing work on the block. So during 1 to 2, what is happening? Work on the system. And one more phenomena is happening. That when it is moving from 1 to 2, then due to friction between the block and this wedge, right, some heat is produced, and that heat is going to the surrounding. Basically during 1 to 2, what is happening? During 1 to 2, two things are happening. Work on the system. We are working against the gravity. So work on the system, correct, and heat rejected from the system. Two things are happening basically. So we reach from 1 to 2, right? Now when it is coming from 2 to 1, then every single phenomena should be reversed. Sir, it is a reversible process. How can you say that? Sir, because when it is coming from 2 to 1, then we are getting work. See, during 1 to 2, sir, we did work on the system, increases the potential energy. By that potential energy, we can again reverse the work. So basically we will get the work, and block will reach from 2 to 1. Right. So work is reversed, but what about the heat? Right? As per definition, when it block is coming from 2 to 1, then it should absorb the heat. During 1 to 2, it is rejected heat, then 2 to 1 it should absorb, then only it will called as a reversible process, but it is not going to happen. Why? Because when it will come from 2 to 1, again some heat will produce, and that heat will go to the surrounding. Is it clear to everyone? So basically what I'm trying to say, this particular system is moving from 1 to 2, again coming from 2 to 1. System may achieve their initial position, but in surrounding 2q amount of heat is there. Surrounding is not their state. Surrounding is basically not in that state. Is it clear to everyone or not? Means it is a irreversible process. It is a irreversible process. It is a irreversible process. Is it clear? So it is a irreversible, and friction is one of the major cause of irreversibility. In thermodynamics, irreversibility is happening because of this friction mainly, right? And few more regions are there. Slowly we'll understand each and every region, but for time being I can say you that from here it is clear that for a reversible process, if process is reversed, then it will follow the same path. And second, very important, it should be frictionless, because if friction will be there, definitely surrounding will affect, and in that case it will be a reversible process. Is it clear to you? Okay, this is a basic introduction actually. Slowly, because reversible process is very important phenomena in our subject, right? Because everywhere we are considering the reversible process only. So slowly we'll understand basically, right? Even some more information will gather after some time, don't worry. Okay, now come to the another classification of thermodynamic process. Now thermodynamic process can be classified as a spontaneous process or quasi-static process. A spontaneous process means natural phenomena which are happening in the universe, which are happening in our system, our earth or our moon, but whatever, in complete universe, whatever natural phenomena are happening, that is basically called as a spontaneous process. Even mostly this word is used for fast processes. Whatever most of the processes are happening in the universe, mostly those are fast process only. Karina, in our sense, sometimes you will feel that it's a very slow process, but actually it is a very fast, because we are going to compare with quasi-static process. You will understand, just wait for some time, right? But spontaneous processes are generally, we can say, fast process. It is what? Fast process. ठीक है? Fast process. It is generally fast. Now what about another one? Is spontaneous, another one is quasi-static. What is quasi-static? See, the word quasi means almost. Quasi word means what? Quasi means almost. This word quasi means almost. It means almost static process. Almost static process means the process is very, very slow. It is a very, very, let's say some piston cylinder arrangement is there and piston is moving, right? Piston is moving, but piston is moving very, very slow. It seems like it is a static, almost static. It is almost static. Clear hai? So this is called as what? Quasi-static process means infinitely slow process. Infinitely slow process in which each and every equilibrium state is defined. Just wait for some time, you will understand what is the equilibrium state, why this statement also you will understand. Just wait for some time. Now, to make you understand about all these four things, like spontaneous, what is spontaneous, irreversible, reversible, quasi-static, what is the relation, everything you will understand when I'm going. And to make you understand this thing, we are going to consider one phenomena. We are going to consider one phenomena here. Let's say we have one piston cylinder arrangement, and in this piston, right? In this piston we have one block. ध्यान से सुनिएगा. Now we have one block like this. It's a block W. Now because of this, here condition is P1 V1. Like here some gas is there, and this gas condition is P1 and V1. Right? That gas condition is P1 and V1. Clear hai? This color is visible, or should I use some another color, right? Should I use some another color, right? Okay, red color I'll use. Right. So we have some piston cylinder arrangement. Please listen here carefully. So we have one piston cylinder arrangement. In that, one big block is there. Now this pressure P1 is obviously higher than atmospheric pressure, because it is a summation of P is because of atmospheric pressure plus due to this weight. Now what I'm going to do, I'm going to remove this block, right? I'm going to remove this block. When I'll remove this block, then what will happen? Then it is actually here there is a huge pressure difference, so because of that this piston will move forward and it will be a very, very fast process, or we can say spontaneous process. So this piston will reach to the top spontaneously, very, very fast. It will reach the very, very fast, and final condition will be P2 and V2. So if I draw the initial position, initial condition in this diagram, so initial condition will be somewhere here, right? This is the initial condition where pressure is very high, that is P1, volume is small, V1. Now when this phenomena is, when we are removing this block, then pressure is basically decreases and volume is basically increases. Now it is a P2, pressure is decreases, volume is increases, V2. This is one state or is two state. Okay sir, I understand. Initial state you drawn in the PV diagram, final state also you drawn. Sir, please draw the process also. No, I cannot draw the process. Why sir? Why you cannot draw the process? Why you cannot draw the process? Very simple thing, because we don't know what are the intermediate states. Intermediate states we don't know. If we don't know intermediate, then we cannot draw the process, because it may be like this, 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 right? The process can be like anything, right? But to draw the process, you must know the intermediate states. So intermediate states are not known. But sir, in thermodynamic analysis, we must know the process, right? Then only it will be useful for us. Okay. If you really wants to know what is the process actually, then you have to go for, this is spontaneous process. This is spontaneous. You have to go for quasi-static process. Sir, how to achieve quasi-static process? Do one thing. Whatever block you have taken here, no, that block you have to divide in infinite number of small pieces. You just assume that here some sand is there and we are removing one by one every sand. Even you can think of that here some packet of rice is there and we are removing one particle of rice. Even rice is a bigger one, right? The actual thought process is like infinitely slow process, like it's a sand or something, very small particles are there. Okay, so now what we are going to do here, initial condition is known, P1 V1, right? Now we are going to remove few. When we will remove one, then what will happen? Then it will look like this one. Then one intermediate state will be known here. Then it is like P1 dash V1 dash. Then here again some molecule will be come out. Then P1 double dash, P2 double dash. Slowly one by one will remove, and after some time our piston will reach to the top. Our piston will reach to the top where pressure and volume will be P2 V2. Now it is a P2 V2. So here we have P2 V2. Now please listen here carefully. In this case, P1 V1 is known, P1 V1 is known, P2 V2 is known, P2, not only P1 P2 V2, not only P1 V1 P2 V2, intermediate, lot of intermediate states are known, right? Infinite number of, ideally infinite number, but actually also many number of states are known, and the series of these equilibrium states is called as was actually process. So this is a path. So if you really defined the path of a process, then the process must be quasi-static. Please listen here carefully. Please listen here carefully. For fast process, intermediate points are not known. You cannot draw the process in a property diagram. You cannot draw. Okay? If you really wants to draw the path of a process, then it must be quasi-static process. Even reverse is also true. Means somewhere let's say path is defined. Suppose some process is drawn in a property diagram, then that process will be quasi-static process, because only quasi-static process can be represented in any property diagram. Is it clear to everyone? Okay. Now the very important fact here, that see here it is a forward process, right? Here it is a forward process, and we are removing the block one by one, right? Now if I start putting, right, this particle, if I start putting particle one by one, then what will happen? The potential difference is so small here in every process. So what is going to happen? Basically this is going to reverse, right? Basically what is happening, please listen here carefully. during 1 to 2, what we did, we remove one very small particle, we reach here. Now if I again start putting those small particles and we try to reach to P2 to 2 to 1, then it will follow the same path. Here if you remove the block, then it will move here. If I again put the block, maybe it will achieve this initial position, but intermediate state will change. Even we don't know intermediate states, even we cannot define the intermediate state. So basically what I'm trying to say that one condition was there. Here I told that if a reversible process, if it reverse follow the same path, and who will follow the same path? Quasi-static process. Means one thing is clear here, mere dost, right? My friend, one thing is clear here, that reversible process must be quasi-static, because only for quasi-static process will follow the same path when it is reversed. Correct na? So one condition is clear here, for reversible. Being reversible, the process must be quasi-static. Process must be quasi-static, and at the same time it should be frictionless also. So plus frictionless. Right? Now one assertion region is asked. One assertion region question was asked in IES. I'm going to share with you. What is the question? Assertion was given. What was the assertion? That all reversible processes are quasi-static, but all quasi-static process need not to be reversible. Tell me. Just comment and tell me. Right. All reversible processes are quasi-static, but all quasi-static process need not to be reversible. It is a correct statement. See here. Whatever reversible, all the reversible process must be quasi-static, but all quasi-static process need not to be reversible. Only those quasi-static processes are reversible which are frictionless. The reason was given that frictionless quasi-static process is known as reversible. True. Is the correct explanation also, and it's a correct statement also. So both the statement is written here, that frictionless quasi-static process known as reversible process. Second statement, all the reversible processes are quasi-static, but all quasi-static process need not to be reversible always. Is it clear to everyone? Okay, let's move further. Now, so this is basically about the thermodynamic processes. Now come to the thermodynamic cycle. Thermodynamic cycle is basically the combination of various processes in such a way that initial and final state of the system is same. Means, let's say here we started from here, this is initial point. Now the process go like 1 to 2, then again 2 to 3, then again 3 to 1. Now this is basically what a cycle, because initial and final point is same, and we know that properties are only and only depend upon the state. Properties are not depend upon the path or something or previous history. So as the initial and final point is same, property is also same. If change of the property for a cycle is 0. Change of a property is 0, because initial and final state is same. Now one more fact I would like to share here. Sometimes students are saying that, sir, suppose this is the initial point and we are moving from 1 to 2, right? 1 to 2 through this process. If I reverse the same process, then we will come to the 2 to 1 same process. Now is it a cycle? Actually no, it is not coming under the consideration of a cycle. Cycle must have to enclose some area. Because it's the same process, and it's a meaningless also, right? Because first why meaningless? Because you are moving from 1 to 2, again 2 to 1, nothing change in the universe, you are at one state only, right? Now the second point is that it is not feasible also. right? Reversing in the same process not feasible. So basically this kind of thing is not feasible. So practically if you see, minimum two processes are required, right? Minimum now this is coming under the consideration of a cycle. This is considered to be a cycle, right? And it is including some area also. At the same time here two different processes are there. Is it clear to everyone? Is it clear to everyone? So this is basically called as a process. And now the minimum number of processes required, minimum number of processes are 2 in a cycle to form a cycle. Acha, I'm not saying that is a practical cycle. Can you, if you ask me, sir, tell me any practical cycle where 2 processes are? No, I don't know. Actually, as of I know there is no such a system which have only 2 processes and form a thermodynamic cycle. No, there is not. Practically there is not. But here question is not the practical one. Here the question is what? Minimum number of properties. As of I know, there were one engine, linear engine, right? There was a linear engine developed in 1884, right? And that is based on a cycle, that is a linear cycle, right? That is a linear cycle, and that 3 processes are there. So that is one of the practical cycle basically, right? Practical cycle where 3 processes are there, one constant volume, constant pressure, and adiabatic, right? So those 3 processes were there. 2 processes, I don't think any practical cycle is there. Okay. So this is all about thermodynamic cycle. Now in this series, like in the basic concepts, in the basic definition part, if you see in the basic definition part, the what do you call the last topic is this one, last topic, that is thermodynamic equilibrium. Now it's a very simple topic, but you must have to understand few things. See, basically our thermodynamics, in thermodynamics we deal with the thermodynamic equilibrium states only. Whenever I am saying that the system in particular state, it means that it is in thermodynamic equilibrium state. See, whenever something is happening in our universe, everything has some reason, right? I am here teaching, I have some reason. You are studying here, you may have some reason, right? So some reason is there basically, right? For example, let's say here in this wire current is flowing, for example. In this wire current is flowing. So what is the reason behind it? Voltage difference or potential difference, right? Now if V1, V2 is same, then no current will flow. If V1, V2 is same, then no current will flow. Similarly, suppose here some heat transfer is take place, right? So what is the reason? Temperature difference. If temperature is same, then heat will not flow. What I'm trying to say, my dear student friends, that you cannot say that the behind the heat transfer the region is temperature. No, it's a temperature different, unbalanced potential is required. The driving force for heat transfer is not temperature, it is a temperature difference. Now if I ask you, you are sitting in one room, right? In that room, is it in thermodynamic equilibrium? Thermodynamic equilibrium means a system is said to be in thermodynamic equilibrium if there is no any unbalanced potential or driving force present within the system. There should be no any driving force or unbalanced potential present within the system, right? Generally we are dealing in thermodynamics. So in thermodynamics we all know, right? In thermodynamics we all know that we are taking 3 type of interaction between system and surrounding, correct? One is heat transfer, one is mass transfer, one is work transfer, right? Heat, mass and work. And if this work interaction, heat interaction, mass interaction taking place between system and surrounding, no problem. Between systems around, no, but within the system it should not exist. Then only we'll say our system is thermodynamic equilibrium. Here this word is very much important. Within the system. This is very important. For example, you are sitting in one room, right? Your room is actually a thermodynamic equilibrium. No, actually it is not. Actually it is not. Why? Because near to the tube light, if you see, temperature is little bit more compared to the region near to the AC, air conditioner. So basically there is a temperature difference within the system itself. System is what? Room. Within the room itself some temperature difference is there. Because of that some thermal energy may transfer within the room. Maybe some pressure difference is there. Because of that some flow may occur, or some work may occur, or something like that, right? Maybe some mass transfer take place within the system, or maybe some chemical reaction is taking place. Maybe you are burning something. You are burning something inside. You are, suppose some petrol is there, you are burning within your room. So chemical reaction is taking place within the system. So actually your system is not in equilibrium. You are getting my point or not? Right. So a system is said to be in a equilibrium when there is no such a potential present within the system. Between system and surrounding it is possible. One student asked me earlier that, sir, you are saying that there should be no any temperature difference for thermodynamic equilibrium. I said yes. Means no temperature difference means no heat transfer. I said yes. It means it is an adiabatic process. अरे हमने कहा no भैया. Whenever I am saying that adiabatic process or something, it is between system and surrounding. There may be temperature difference between system and surrounding possible, feasible. There is no relation of thermodynamic equilibrium between system and surrounding. Thermodynamic equilibrium means within the system we are talking about. Within the system there should be no, suppose for example one question is given, in that given that 10 kg air of 20 degrees centigrade. So 20 degrees centigrade is not the temperature at a point in the room. It is everywhere in the room is 20 degree temperature. That is the meaning of equilibrium. You are getting my point or not, right? So to achieve the thermodynamic equilibrium state, three type of interactions are possible, right? Three type of interaction may possible within the system. So to meet the condition of thermodynamic equilibrium, three type of equilibriums are required. The very first is thermal equilibrium. Thermal equilibrium means equality of temperature. Means suppose you are saying that this room is thermodynamic equilibrium, means temperature of the air present in the room should be same everywhere throughout the room. Throughout this room it should be same everywhere, means no thermal energy transfer or heat transfer within the room. Clear hai? Second one is mechanical equilibrium, means equality of all those properties which may cause work transfer, like pressure, force, even some more properties are there. Later on you will get to know when we'll discuss the work transfer, right, work definition in thermodynamics. Then you will get to know there are some more potential differences where due to which work transfer may take place. But whatever potentials are there, it should be same, means there should be no any work interaction. And last one is chemical equilibrium. Chemical equilibrium means there should be no any mass transfer within the system, as well as there should no any chemical reaction take place within the system. Like suppose in your room some fuel is burning, so it is, then we'll say your system is not in equilibrium. So our system, our thermodynamics laws and everything is deal with the thermodynamic equilibrium states. So whenever we are talking about thermodynamics, so whatever states are there, that should be in equilibrium, and all these three conditions should be satisfied. Generally when we are analyzing the IC engine, right, if you remember IC engine, so within the IC engine fuel is burning. Means chemical equilibrium of the air present within the system is actually changing. Correct? A chemical equilibrium condition is not satisfying. So how to analyze, sir, in that case? How to apply first law, like laws of the thermodynamics? In that case there is one assumption. If you, when you study that IC engine part, then you will get to know. Clear hai? You will get to know, beta. What you will get to know? Listen here. What you will get to know? You will get to know one assumption is there. What is that assumption? That assumption is very, very simple. That the combustion phenomena is not considered. Listen here carefully. The combustion phenomena is not considered in the analysis, and the combustion is replaced by equivalent amount of heat addition process. In actual system, within the system, combustion is taking place. Let's say 100 kilojoule of heat is produced due to that combustion, right? Due to that combustion. But in analysis, we will not consider that combustion. We will assume that this 100 kilojoule heat is added externally. The 100 kilojoule heat is added actually externally. That we will consider here. You are getting my point or not? So ultimately I can say that a system is said to be in equilibrium when these potential difference should not exist within the system. Between system and surrounding can exist, but within the system it should not exist. That is basically what thermodynamic equilibrium state. So I hope you understand all these definitions. So up to now we already discussed the basic introduction about the thermodynamics, how to study, and basic definition like system, surrounding, boundary, properties, processes, states, cycle, thermodynamic equilibrium, all these things we discussed. Maybe in GATE point of view, direct question may not ask from these topics, but definitely it is very important to understand the next topics, I would say. So the next topic will be ideal gas and its properties, that we'll discuss in next lecture, right? So if you like the lecture series, and if you want us to make such a series and practice sessions and all, then I just want to request you, please make one a small heart in the comment box. This is the only thing that you need to do. Whenever you are watching any of my video, and you really like it, if you really like it and if you really feel that no, it actually helping you in your preparation, then you can make one small heart in the comment section. Thank you very much. Jai Hind.